So in the last video, I promised to give an example as to when we're doing rational exponents where the numerator is something other than 1, I said I prefer to take the root part first and then do the take care of what was in the numerator. So for example, let me bring it back. We had a to the 2/3, and I said I'd prefer to rewrite this as a to the 1/3 uh, squared instead of saying because I could have rewritten this as a squared and then taken the cube root, right? I always do this way, the top way. Not that the bottom way is incorrect. It's not. They're both equally valid. They're both true. But I'll show you an example as to why this way might actually be really hard to do in some cases. So let's back up here and do real number. Let's do, whoop, that's from the last video rather. So let's say we have 64, right? 64 to the 2/3 power. If we write this as 64 to the 1/3 power and then square it, it's not too hard. 64 to the 1/3 power, we have to think of, it's the cube root of 64. We're saying what number times itself 3 times gives you 64. And this isn't an arithmetic lesson, so I'm not going to go over why, but it's 4. 4 times 4, 16. 16 times 4 is 64. So 64 to the 1/3, or the cube root of 64 is 4. And then we're squaring it. We get 4 squared, that's 16. So 64 to the 2/3 power is just 16. But if I tried writing it the other way and did 64 squared and then took the 1/3 power, well, we have to square 64 in that case. And then we have to take the cube root of a huge number, right? 64 squared is a big number. Sorry, I gotta bring up my calculator here. And let's look at it. So if we did 64 squared, it's 4,096, right? And then, I mean, I don't know by heart that the cube root of that is 16, but it turns out it is. I couldn't do it here with this calculator. At least I don't know how to do it in this calculator. But yeah, if you took the cube root of 4,096, it will be 16. A way to show that is if we cubed 16. So I don't have a cube root button here, but I could do 16. I could cube it, and we'll see that it's the 4,096. So I can write 16, then this little button next to the y lets you pick the exponent. So 16 cubed is 4,096. So yeah, imagine doing that on a test, right? Yeah, that's not something you want to do. You want to stick with smaller numbers, so it's always easier to take the root first, then apply the exponent that's in the numerator position. Okay, so now that that's out of the way, let's actually do some other examples. So I wanted to do examples in this video. I did one with an explanation as to why I do it in a particular order. But let's do some other examples. So what happens, let's do an easier one. What happens when you have, I'll do a real number here, 4, right, to the negative 1/2. How do we deal with that? Well, the way I was splitting up numbers before in the exponent and as a product of two numbers, we can continue doing that actually. We can write 4 to the negative 1/2 is actually saying 4 to the negative 1 times 1/2. Sorry, I meant to write it as rather negative 1. Make sure we can see that. Negative 1 times 1/2. And then we can split it up as 4 to the negative 1 to the 1/2, or we can write it as 4 to the 1/2 to the negative 1. It might look like I'm breaking my rule that I just showed you how to do, because I said I always do the root first and then apply the negative. In this case, I guess I know that it's a really small number, so it doesn't make that big of a deal. But let's look at both cases. So if we did this case here, right, what's 4 to the negative 1? Well, you either know this or you don't. If you watched the video I made on exponent properties, we learned that the any number raised to the negative 1 is actually, the negative 1 says take the reciprocal. So what's the reciprocal for? it is 1/4. So that's 1/4 to the 1/2 now. And then the other rule or property that I covered, one of the other properties I covered, is when you have a fraction in parentheses and then you have an exponent on the outside, the exponent gets applied to both the numerator and the denominator. So this equal, I should write an equal sign here. This should be, I don't even need the parentheses now, 1 to the 1/2 over 4 to the 1/2. So what is the 1/2 power? Remember, it's take the square root of. So what is the square root of 1? Well, it's just 1. What's the square root of 4? 2. So 4 to the negative 1/2 turns out to just be 1/2. So what if we did it the other way? Do we get the same answer? I mean, we should, right? I said this and this are equivalent. We should get the same answer. Well, let's look at it. This says 4 to the 1/2 power. That's just 2, right? That's 4, square root of 4. That's 2. 2 to the negative 1, right? We said, well, if you take anything to the negative 1, it says take the reciprocal. What's the reciprocal of 2? It's just 1/2. So actually this way, we got the answer a lot quicker, which is the way I prefer. But I wanted to show you can do it both ways. So the way I prefer ends up being quicker in this case too. Whoop. So 1/2, 1/2. We get the same thing. Okay, let's try one that's not as easy. So what if we have, let's see. So if I had 1 over 27, okay, all to the negative, let's see, 4/3. All right, we've got a lot going on. One, the base is a fraction. We have a negative exponent. The exponent is rational. Not only is it rational, but the numerator of it is bigger than the denominator. But we can handle this. I always like to, I guess in this case it's kind of a lie because I applied the root first. But honestly, when I do have negative numbers, the negative exponents, I like to get rid of the negative right off the bat. So maybe I break my rule in this case. So in other words, what I'd like to do is write this as 1 over 27. Now, you don't have to, right? This is my preference. You'll develop your own preferences the more you do math and the more you get experience with these types of problems. You come up with your own preferences, but this is mine. So I would write it like this. 1 over 27 to the negative 1, and then 4/3 on the outside, right? And why could I do that, right? Remember, I can, using that property, you take the product of those two, the product of those two, so you can split it up as, using the parentheses, you can say take the base to that power first, and then after you do that, take it to that power, right? So 1 over 27 to the negative 1, well, that just ends up being 27. Why? Because negative 1 says take the reciprocal. What's the reciprocal of 1 over 27? It's just 27. And then we want to take it to the 4/3, but I'm going to do to the 1/3 first, right? And then to the 4th, right? Applying the root part first. It's just easier to do it that way. What is the, so 27 to the 1/3 is the same thing as saying what's the cube root of 27? Well, it turns out to be 3. 3 times 3 is 9. Times 3 one more time gives you 27. So that's 3 to the 4th power. Okay, well, to figure that out, that's just 3 times. We already figured out that 3 times 3 times 3 was 27, but then we have one more 3. So we could think of that as, the easiest way is 3 squared times 3 squared, right? So in other words, write this as 3 squared. I think that's easier to deal with. Or you can write, like I just said, that's the same thing as saying 3 to the 2 plus 2, which is 3 squared times 3 squared. I think that's the easiest way. 3, so you can look at it this way. 3 squared is 9, right? So I applied this, and then you have 9 squared, and usually people know that 9 squared is 81. right? This way, over here, you get 3 squared is 9 times 3 squared is 981. So these are all, you're pretty much doing the same thing, but that's how you get these types of answers. Break it up into things that you know what they are. Break it up so that you know what the answers are bit by bit, so you can get to the final answer there. So we see that 1 over 27 to the negative 4/3 ends up being 81. Okay, let's do something a little bit different here. Let's do a to the negative 3/4 divided by a to the 2/3. Okay, this might look really scary, but if we apply the exponent properties that we learned in the last video, or I shouldn't say the last video, but in the videos I did on the exponent properties, right? We know that when you have the same base being divided by itself, you can subtract exponents. You always subtract the exponent in the denominator from the exponent in the numerator. So that means this is a to the, what's the exponent in the numerator? Negative 3/4 minus, there's our subtraction, right? 2/3. Well, in this case, you have to simplify that exponent by doing the subtraction. Now, if your fraction addition and subtraction isn't all that great, this is why you need to work on it, right? You get these types of problems that involve things you've learned previously. It's not like once you've learned something and have fractions and then you move on and then you never see them again. No, you see them all the time. So you're going to want to work on that if you're not good at this already. So we can do this off to the side. This is negative 3. Oops. Write that a little cleaner. Negative 3 over 4 minus 2 over 3. We want to get a common denominator. I'm just going to use cross multiplication. In cross multiplication, you multiply denominators together. So 4 times 3 gives you 12. Then you cross multiply. So I get this denominator times that numerator. 3, and then I have a negative 3. That gives me negative 9. Then minus, because it's subtraction, minus 4 times that 2 there gives us 8. And I end up with negative 9 minus 8. Right, so it's a negative and then minus a number. That gives us negative 17 over 12. Excuse me. So the answer here, let me simplify this. This is a to the negative 17 over 12. Now, is that the final answer? No, it's not. In fact, what we can do is get rid of that negative sign in the exponent by applying it, right? That means this is a to the negative 1 all to the 17, positive 17 over 12. Right, I took the negative 1 out and I took it as a product of negative 1 and 17 over 12. A to the negative 1 is just, I'm going to write it over here, and I'm going to change colors because it's getting boring. A to the negative 1 is 1 over a. 1 over a. And we have this exponent here of 17 over 12. But I'm going to write it a little bit different for a reason. Because we went over this before. We have a numerator that's bigger than the denominator. I want to write it this way on purpose. I want to say 17 over 12 is actually 12 over 12 plus 5 over 12. The reason I want to write that is because I want to get rid of, right, one of these factors here. Because you have a to the 12th power means the 12th root of a. But if I have at least 12 12th roots, they're going to end up canceling, just like the square root of a times the square root of a gives you a. Because there's 2 of them, you're taking the square root, just they combine and give you 1a. If you're taking the 12th root of a and you have 12 of those, multiplying them all together is just going to give you a. Well, it's going to give you, whatever the whole number is. I guess 1 over a, sorry. Excuse me. So here, I can rewrite this, by the way. because I have a sum of exponents, I can write this as 1 over a to the, well, 12 over 12, I can just write that as 1, right? That just simplifies as 1. So it's 1 over a to the first power times, remember when you have a summation here, you just write as the base times itself, right? Where the two different numbers across the plus sign are the exponents. So that becomes 1 over a times, this is the 5/12 here. I can't simplify that any further, so that's just 5/12. Okay. What is 1 over a to the first power? Well, that's just 1 over a. 1 over a. What's 1 over a to the 5/12? Well, here we have an exponent, right, on the outside of parentheses. That means, and we have a fraction inside. You apply the exponent on both the numerator and the denominator. So we have 5/12 on the 1. Well, what is 1 raised to the 5/12? Well, that's taking the 12th root of 1, which is just 1, and then raising it to the 5th power. 1 to the 5th power is just 1, so it's just 1. So we get 1 over a times 1 over a to the 5/12. A to the 5 over 12. And then if you wanted to, you can combine that into just 1 over a to the, now this might be a situation where you might want to write this as a root, just to kind of combine it all into one. So instead of having an exponent form, we're going to write in what's called root form, right? So I will write the 12th root, write a little 12 there, of a to the 5th. Remember, the 5th, I can write, let me make that a little bit cleaner. I can write the 5th on the inside or the outside. Remember, from the last video, it doesn't actually matter. Trying to write this clear enough. Here we go. A to the 5th. That's one way to write it. Another way to write it, honestly, is, I'm just showing you different ways to write it because they're all kind of valid. It really depends, because the main thing is you always want to write things as simplified as possible. But is this truly as simple as it gets? Because another way to write this would have been to just leave this as 1 over a to the 17 over 12, right? And then that would have ended up being 1 over, and do this on your own and prove to yourself that this is true. That would have been the 12th root of a to the 17th. Is this simpler or is this simpler? I don't know, right? Honestly, it doesn't really matter, because your teacher would give you credit for both because they're the right answer, and there's as simplified as it really gets. There's not a lot you can do except exchange, or I should say go back and forth between these two, and it's kind of subjective at this point as to which one's more simplified. Okay, I'm gonna do yet another video with more examples because I can't keep making like a 30-minute video, because I want to do more examples because these things can get tricky, and I want to show you a wide range of problems like this. Okay, see you in the next one.